This is our first video from section 4.6, Modeling with Exponential Functions. In this video, we're going to talk about doubling time and relative growth rate, and we have a couple more topics next week. Many processes that occur in nature, population growth, radioactive decay, heat diffusion, and others, can be modeled by using exponential functions. In this section, we're going to study some exponential models. Remember that exponential growth is growing by a certain percentage, maybe per year or per day or per hour, rather than by a fixed amount, which would be linear. And if you just think about the way population grows, the larger the population, the faster it's going to grow. So we do want to express it with that percentage growth, just like we did with compound interest and earning interest on interest. Let's talk about exponential growth and doubling time. Suppose we start with a single bacterium, which divides every hour. How many bacteria do we have after 1 hour? Well, let's see. After 1 hour, if we start with one bacterium and it divides, I'm going to have 2 bacterium after 1 hour. In 2 hours, well, after another hour passes, these are each going to split. So it looks like 4. After 3 hours, well, each of these are going to split into 2 more bacteria. That's 8. And it appears if we're doubling every hour, we're multiplying by another factor of 2. We have created exponential functions in this way before when we first introduced the definition of an exponential function. See, we can model the bacteria population after t hours. F of t equals 2 to the t. So after t hours, 2 to the t bacteria. And if we start with 10 of these bacteria, well, we have that factor of 10. We can rewrite our population model in this way, 10 times 2 to the t. That should be familiar also. If we have a slower growing strain of bacteria, and that strain starts with 1 and doubles every 3 hours, well, how many after 1 hour, 3 hours, 6 hours, 4 hours, t hours? Well, the easy one's in here. After 3 hours, if we started with 1 and we double every 3 hours, we should have 2 after 3 hours. And after another set of 3 hours, we should have 4, right? So this was just 2 to the 1. This is, well, 2 sets of 3 hours, or really, if I look at 6 divided by 3, that's 2 sets of those 3 hours are in 6. These get a little bit trickier, but after 1 hour, I'm thinking we still want to figure out how many sets of 3 hours are in 1 hour, and that's just 1/3. Over here for 4 hours, well, if I take 4 divided by 3, it'll double once, and then a part of a doubling, 1/3 more times. It looks like a pattern here is 2 to the, well, t over 3. That would tell you however many hours you start with, divide it by 3 to figure out how many times it can double in that amount of time. And that's your power on 2. So generalizing this, here's a formula for exponential growth involving a doubling time. If the initial size of the population is n naught and the doubling time is a, then the size of the population at time t is n of t equals n naught times 2 to the t over a. A and t are measured in the same time units, so we were looking at hours, but it could be minutes, days, years, and so on. Remember notationally here, 2 is our base, and it's multiplied by n not after we take the power. So let's be careful about our order of operations in using an expression like this. But here's our initial population, 2 to a power, and since it was not doubling just every hour, but every 3 hours or maybe every a hours or a days, we have t divided by a. Let's do an example. A certain culture of the bacterium Rhodobacter spheroides initially has 25 bacteria and is observed to double every 5 hours. Find a model for the bacteria population after t hours. So let me write this down just as a reminder. N of t was our initial population multiplied by 2 to the t divided by our doubling time. In this case, our initial population is 25 bacteria. We're multiplying by 2 to the t over 5 because that's our doubling time. This should work for any amount of time t. So how many bacteria in the colony after 18 hours? Well, n of t is 25 times 2 to the 18 over 5. Again, that's divided by 5 because I need to know how many times 5 hours goes into those 18 hours. It's going to double 3 times and then a little bit more. Let me get a decimal approximation of this. Again, be careful of your order of operations and parentheses as needed. I get, rounded to the nearest bacterium, about 303 bacteria. So it started at 25 and it's doubled 3 times, and then there's a little bit more growth. If you're plugging this in your calculator and you're not getting this value, make sure to ask me and see what's going on. After how many hours will the bacteria count reach 1 million? Well, gosh, let's see. 1 million is what I want my population n of t to be. So let's write this equation down, and we want to solve for t to figure out when we're at 1 million. So again, careful of my order of operations here. I can't divide by 2, it's attached to this exponent. I can divide by 25. 1 million divided by 25 is 40,000. Then I can do natural logs. That'll be t over 5, natural log of 2. Multiply by 5, divide by the natural log of 2. This is my t value. That's approximately 76.4, and this is in time in hours. After about 76.4 hours, our bacteria will reach 1 million. Pretty fast growing. All right, let's try one more. This is a little bit different. A bird species was introduced in a certain county 25 years ago. Biologists observe that the population doubles every 10 years. Now the population is 13,000 birds. So this is interesting. We're given a current population, we're given a doubling time, although I'm not sure we're given an initial population. So let's see if we can figure out what is that initial population. I'm going to bring my model into play here. This will be n naught times 2 to the t over 10, because we know it doubles every 10 years. This is my a value. I also know, well, if the population was introduced 25 years ago, after 25 years we've got a population of 13,000 birds. I can think of that as an ordered pair. When t is 25, the population n of t is 13,000. And I'm wondering if we just plug this ordered pair in, if we can create an equation that we can solve for n sub 0, which is our initial bird population. Let's give that a try. So n of t, or n of 25, is 13,000. That's n naught times 2 to the 25 over 10. Sure, we should be able to solve this for n naught. Our initial population is just 13,000 divided by 2 to the 25 divided by 10, or 2 to the 2.5. And let's get an approximation for that. That's about 2,298 birds. Makes sense, it should be smaller than what we have now, which is 13,000 birds. 25 years ago, there were 2,298 birds. We can use this to estimate the bird population 5 years from now, because now I have an entire function. N of t is 2,298 times 2 to the t over 10, and in this case 5 years from now, if we initially started 25 years ago, my t value is going to be 30. Let's approximate this. 2,298 times 2 to the power of 3. 5 years from now, I expect the population to be about 18,384 birds. Just to keep in mind what's going on graphically here, let's sketch a graph of the bird population. Let me bring our function over here. It was 2,298 times 2 to the t over 10. We have a little bit of information. We have the point 0, 2,298. We've got the point 25, 13,000, and we've got the point 30, 18,384. As I draw this, I know that I want to stay just in my first quadrant here. I'll label my axes, and maybe we'll count by thousands here. 2,000, 4, 6, 8, there's 10,000, 12, 14, 16, 18, 20,000. And maybe I'll count by fives this way. All right, 0, 2,298, 25, 13,000. It's going to be right around in here, about there. And 30, 18,384 is going to be right around here, about here. And since it's exponential growth, I'm expecting this upward curve. Something like that. I'd like to talk about something different than doubling time here. Let's talk about exponential growth and the relative growth rate. A few things to discuss before we dig in. We've used an exponential function with base 2 to model population growth in terms of the doubling time. That's a common thing to do. We don't always have doubling time. We could certainly model the same population if I had a tripling time. We could do it with an exponential function with base 3, or a quadrupling time. We might use base 4. We could find an exponential model really with any base. If we use the base e, what we end up with is a population model in terms of the relative growth rate r. That is the rate of population growth expressed as a proportion of the population at any time t. In this case, we can think of r as an instantaneous growth rate. That's going to be more precise when we get to calculus. But for example, if r is 0.02, then at any time t, instantaneously, our growth rate is 2% of the population at that time. Here's what it would look like to create a model with a base e. Population experiences exponential growth, increases according to this model, n of t equals n naught e to the rt, where r, again, is that relative rate of growth as a proportion of the population. This should look kind of familiar. It's the same as that PERT formula that we used for continuously compounding interest. And yeah, it is the same thing. The same idea is at work in both cases. The growth of a population or an investment per time period is proportional to the size of the population or the amount of the investment. Again, if you have a larger population, it'll increase more than a small population will. That's why we wanted to use percentages. Same way, an investment of $1 million will increase more in 1 year than an investment of $1,000. Let me show you how this exponential growth with a relative growth rate might work in an example. And then I want to just do a little bit of comparison. Can we write one situation both with a base 2 doubling time equation and a relative growth rate? And how do they compare? A fish population in a certain lake has a relative growth rate of 3.5% per year. It is estimated that the population in 2012 was 4,000 fish. Write an exponential function to model the fish population t years after 2012. Then predict the population in the year 2020. Since I'm given a relative growth rate of 3.5% per year, that's what clues me in to the fact that I want to use this model with a base e. N sub 0 is still our initial population. If we're looking at t as years after 2012, that means our starting population is 4,000. So let me see if I can fill in some of this model. This is 4,000 e to the r is our relative growth rate. I'm going to express it as a decimal, so it's 0.035 t. Here's our model. If I want to use it to predict the population in the year 2020, that's a t-value of 8 since we're starting in 2012, 2 years after 2012. N of 8 is 4,000 e to the 0.035 times 8. Plugging this into the calculator, I get about 5,293 fish. Makes sense to round this to the nearest whole number because I'm not going to have a fraction or decimal of a fish. So 5,293 fish in the year 2020. With this example, I'd like to model a population. I want to do it both with our base 2 model and then also our base E. And just think about a little bit of a comparison. The population of a city was 112,000 in 2014, and the observed doubling time for the population is 18 years. So part A here should be pretty simple, finding the exponential model with base 2, because I'm given a doubling time. Here's my value A. Remember, our model is going to look like n sub 0 times 2 to the t over a. A is 18, n sub 0 is our initial population, and if we start in 2014, that's going to be 112,000. So I think we've got a model here pretty easily. This is 112,000 times 2 to the t over 18. Let's try this again and find an exponential model with base e to model the population. Again, our previous model with base 2 was 112,000 times 2 to the t over 18. Let's just kind of keep that in mind as we compare here. Our base e model looks like n sub 0 e to the rt. This is a little bit trickier because, yeah, I'm given a value for n sub 0, but I'm not given a value directly for r. So I can fill some of this in. N sub 0 is 112,000. E to the RT. If you take a look at our previous model, what's different is this 2 to the t over 18 power as opposed to e to the RT. And if we really isolate this, I really want these to be the same thing. Or even more precisely, 2 to the 1/18th, I want to be the same as e to the r. If I take these both to the power t, I get this, so I'm undoing that. I need these to be equivalent. I think this is an equation I can solve for r. If I use a natural log, the natural log of 2 to the 1/18th is r. And that's about 0.0385. Now I'm ready to complete my model. In terms of a base e, my model is 112,000. E to the 0.0385 t. If you want to put the whole exact answer up there, the natural log of 2 to the 1/18th, you can. This decimal approximation is what you'll typically see. The reason for that, I think, is because we can interpret what that tells us. That actually gives us our relative growth rate of the population, which is our next question. What is the relative growth rate? Well, that exponent was 0.0385. So the relative growth rate is about 3.85%. Notice that's new and valuable information. If you look at the original statement of the question, we were just given the population in 2014 and the doubling time. And through this calculation, we were able to determine what that relative growth rate was. So an important kind of calculation and comparison. One model, if we look at both models, one model allows us really easily to see what the doubling time is. The other model allows us to really easily see what the relative growth rate is. So both are useful. I brought both of our models forward to take a look at this question. And actually, I apologize, I need to change this a little bit. I meant to say, when will the population reach 200,000? Excuse me, I left 1 0 out. I should be able to use either equation to solve this. I just need to set it equal to 200,000 and solve for t. Let's do both just to be clear and know that we get the same thing. So let me try 200,000 equals 112,000 times 2 to the t over 18 first. I'm going to divide by 112,000. If I do that and reduce the fraction, it's 25 over 14. Then I'm going to use logarithms. How about the natural log? All I need to do now is multiply by 18 and divide by the natural log of 2. This is about 15.06 years. If I do it with the other equation, 200,000 equals 112,000 e to the 0.0385t, I expect to get the same thing. Just to verify again, if I divide by 112,000 and then do natural logs, the natural log and the base e will cancel out. So this is just 0.0385t. So t is the natural log of 25/14 divided by 0.0385, which again is about 15.06 years. Check it, make sure you believe it, but it should be.